All right, we're going to finish up section 6.3, and the part that we had left off on was going to move us into a discussion of exponents. And the reason exponents occur here is because what exponents are is multiplication by something a repeated number of times. So that's why they're occurring in this section on multiplication and division. All right, so we are going to first see if you guys remember, and if you don't, it's okay, what a definition of an exponent is. So if we have, and some of you are a little shaky on this just because some of the questions I heard you asking today. If you have a value raised to the power of n, what it means is it's that value multiplied by itself however many n is number of times. So it's a multiplied n times. So when we have written down 5 cubed, it means 5 times 5 times 5. If we have written down x cubed, it means x times x times x. Okay, it doesn't matter what it is. It means it's multiplied by itself that number of times. So now we get a chance to try and remember. You guys are going to help me fill these in. These are theorems or properties of exponents, and I'm actually going to justify for you why each of them works after we remember what they are. So do you remember what you do to combine a to the m times a to the n? You do something with the exponents. What do you do with them? You add them. What do you suppose you do when you divide them? You subtract them. How about when you have an exponent raised to another exponent? You multiply them. 4 and 5 have sort of a, excuse me, a distributive flair to them. So when you have a b to the m, it's just a to the m, b to the m. And when you have a over b to the m, it's a to the m over b to the m. And if you think about both of those, what you hopefully notice as you look at them is there is no property that says what happens if you have a plus b to the m. Right? There's no property for that. You can't distribute the exponents on everything. You only have the ability to do this sort of distribution of exponents for multiplication and division. It's very specific. All right, the last one here, number 6. How is it different than number 5? So negative. Do you remember what negatives do? They flip fractions. So instead of having a to the m over b to the m, we'll have b to the m over a to the m. Okay, it's going to flip it. All right. Yes, Hannah.
Like if you're doing a problem or something and you see a to the mn, that means it's going to be multiplying, whereas you're going to see it when they're adding it, it's always going to be m plus n. You're not going to get those confused.
Right. So whenever we have variables that are just beside each other, next to each other, it automatically means multiplication.
Okay.
That is a mathematical convention that's used frequently. And you know it. I mean, you've used it before. It's the same thing that happens when you write down 5x. What is 5x? Well, it means 5 times x, but we sort of drop that multiplication notation very quickly because it becomes sort of annoying to write. And that's really it. It becomes annoying to write. So whenever we have numbers next to a variable or two variables next to one another with no symbol between them, we mean multiplication. Okay, what I want to do next is we're going to go through each of these 6 rules, properties, theorems, whatever you want to call them, and I'm going to justify for you why they each work. I don't justify for you why they each work because I expect that you're going to be teaching your children in your classroom why they work, but you will have that one kid that wants to know why something works. And even if you don't remember it off the top of your head, I'd like for you to be able to say, you know what, I will bring that back to you tomorrow and I'll show you why it works. And you have the resources to be able to go find that information, okay? Because you are going to have that one kid. Maybe not every semester, let's hope not. But every now and then you're going to have him in class or her in class, okay? All right, the first one that we're going to look at is the one that is a to the m times a to the n. And you guys told me this is a to the m plus n, right? That's what you told me it was going to be. And so I'm going to do some examples, and I'm actually going to use, these are not like formal proofs of mathematics or anything. They're just examples trying to show you why things work. All right, so we're going to do the example of a to the 3 times a to the 4. This is my justification example. All right, according to the definition of exponents, what does a to the 3 mean? Correct. And what does a to the 4th mean? How many a's do you have? 7 of them. So this is a to the 7th. And how do you get from 3 and 4 to 7? You add them. That's exactly how simple this process is. Okay? Next one looks a little bit different. You guys, again, told me that this is subtraction. So we're going to do the example of a to the 5th over a squared. Okay, you guys know how to do this. What is a to the 5th? Yeah, lots of a's. And it's divided by a squared, which is a times a. And back in the first section of chapter 6, 6.1, we learned that if we have things multiplied together on top, things multiplied together on bottom, we have the ability to reduce fractions, right? So I don't care which of the two you want to reduce it with, but it's going to reduce with one of them because it's multiplication, right? It's multiplication there. And that leaves me with 3 a's on top. And how do I write 3 a's multiplied together? A cubed. So how do I get from 5 and 2 to 3? Subtract. All right, our next one. This one is sometimes confused with the first one. So let me go back over here and just make note with you. How are 1 and 3 different on the left-hand side? How does this look different than this one?
There's parentheses.
There's parentheses. That's a good point. What else?
And doesn't have a base of A.
There's not a second base of a, right? One of them has a there twice and the other one doesn't. Okay? So just being aware that that's how they look different. So we're going to justify now why this one is multiplication. And the example we're going to use is a to the 3rd to the 2nd. All right, so what is a to the 3rd? A times A times A. And what does it mean to square something? To do it twice. So now I have A times A times A and another A times A times A. I've currently got them written in parentheses. They don't really have to be. I'm just making sure you see that that's where they came from. But how many A's do I actually get out of this? 6. And how do I get from 2 and 3 to 6? Multiply. All right, our next one, number 4. This one, we ended up using what we sort of said looked kind of like something called distribution. And the example I'm going to do is going to have that exponent be just a 3. Okay, so just like you told me a moment ago, squaring means multiplied by itself twice. This is cubing, so it's multiplied by itself 3 times. So it looks like this is what it really means, right? But you have this wonderful property in mathematics, and it works for all of our number systems, and it allows you to switch the orders of things around with multiplication and with addition. It doesn't do with subtraction or division, but multiplication and division it does it for. Do you remember what that property is called? Commutative. That's right. The commutative property lets me change the order of things. So instead of it having it A, B, A, B, A, B, A, I think that was enough of them. A, B, A, B, A, B. I can actually put all the A's at the front. And I can put all the B's in the back. And that's actually 2 properties in one. It's the commutative property. It's also the associative property because there were some parentheses here in what I was doing my ordering. But again, I get associative property from multiplication. And then you can see that I have A cubed, B cubed. And we compare that to the AB, to the quantity cubed at the beginning, and we have our property. Okay. 2 more. Okay. This one is even cleaner than the last one, to be honest. So this is A to the M over B to the M. And we're going to use as an example A over B cubed. So So just like on the last slide, we can write this as a over b times a over b times a over b. But multiplication of fractions says then that I just multiply across the top. I multiply across the bottom. I don't even have to reorganize or restructure or anything. And I see my a cubed over b cubed coming into play. Okay, any questions on that? Okay, the last one of this set, anyway, is ab to the negative m, and we said that's b to the m over a to the m. And I'll do the same example basically that I did above, just with a negative 3 exponent instead of a positive 3 exponent. All right, so the first thing I'm going to do is going to feel a little bit awkward, but just bear with me for a moment. I want to rewrite negative 3 as 3 times negative 1. Okay? That's negative 3, right? I mean, like, it feels maybe like weird, why did I do that? But it's true. And then I'm going to use the property of exponents that was number 3. And I'm going to rewrite this as a over b cubed, and then the negative 1 power out here. I'm using the third property in reverse. I'm starting with something that's multiplied together, and I'm separating it out as multiplication of a fraction to a power to another power. All right, so the part that's in the inside we've already done. We know that that's a cubed over b cubed. We know that. Okay? And then the negative 1 is inverse, means multiplicative inverse, or it means reciprocal. So that's where we're going to get to flip it upside down now. So now I have b to the third over a to the third. There are 2 additional exponential facts that I want to show you. Any questions on these slides before I go to those 2 additional ones? Okie dokie. The 2 additional facts I want to show you are a to the 0. In number theory, we just say this is 1 and we're done, and we don't justify anything. We use it as a definition. But we've got enough information now, and we've built up enough in our number system by the time we get to this class, I can justify for you why this actually works. Okay? Do you know what the other one is? It's kind of a variation of the last one we just did on the last slide. What is a to the negative n? Do you remember?
1 over a.
Right. 1 over a to the n. And again, we can justify that one too. All right, so let's talk about the a to the 0 power. And what I'm actually doing on this one is, it actually is a proof. This is not an example. I'm not using any particular numbers. This is actually a proof that this actually works. So what I'm going to do is I'm going to write down a to the 0. I'm going to start on the left-hand side of this equation. And when I'm all said and done, the right-hand side is going to equal 1. Okay? So we're going to do something, and it's going to look a little funny. We're going to rewrite 0 as m minus m. Okay, so 2 things. Yes, it looks funny. And then number 2, it's still correct, right? It's a true statement. Then I'm going to use the property number 2 of our properties that we had before, and I'm going to rewrite this as a to the m over a to the m. Isn't that also true? That's property number 2 in reverse. Well, what happens when I divide something by itself? It's 1. Now you know why a to the 0 is 1. It's not just because it was nice and somebody decided it. It actually is true. It really works. You've got a very short, very, very short little proof to show why. All right, the other one, I'm going to do it with an example. And we're going to do a to the negative 3. All right, so we already talked about, well, actually I'll write it out. Negative 1 times 3 like I did before. And then we can write this as a to the negative 1. This feels a lot like that other one we had, but to the third. We already talked about the fact that a negative exponent means reciprocal or multiplicative inverse. And so the multiplicative inverse of a is 1 over a. And then this is cubed, right? We could have done the cubing instead of the negative first. I just did it the other way around because I wanted to show you it didn't matter. And then according to property 5, this should be 1 cubed over a cubed. But what is 1 cubed? It's 1. So we end up with the 1 over a cubed when we're done. Okay, so again, I'm going to reiterate one more time, and I'm going to state it a little bit differently. I didn't show you these examples because you're going to teach it in class every day. And I also didn't show these examples because I expect you to rewrite everything without exponents in the problems you work with. That's not my point at all. So as we are working these problems that are next, we're using the properties that we just encountered. I don't want you to have to write things out multiple times and things like that. That's not the point. The point is to be able to use the properties, but to recognize that they actually come from somewhere and they make sense. All right, so what we're going to do is we're going to write the simplest form with positive exponents for each of these fractions, okay, for these rational expressions. So I have ab to the 4th over a to the negative 3rd b squared. And there are multiple ways to do these problems, okay? So first of all, let's just get that out there in the open. So if I suggest to you to do the problem one way, or that's how I think of it, and you're thinking of it another way, feel free to ask, would this work too? Because there's a good chance it probably would. So somebody give me a suggestion of what you see when you look at this problem of how you might do it. What would you do? What could you do?
I would try to like separate the A and B so that you can like line out, like cancel out.
Okay, so I'm just going to draw kind of a squiggly thing in between them.
Like
Just sort of ignore them.
A times B times B times B times B.
Oh, we don't want to do that. We don't want to write the b's out. We have no desire to do that. We want to use the properties that we have from before. Okay, we want to make it as easy on ourselves as possible. So I like the idea of separating these though. So let's just only look at the a's. So ignore the b's for the moment. What could I do with the fact that I have an a on top of an a to the negative 3rd? You're on the right track with the negative part of it, but see the a on the top doesn't have a negative exponent. You can only move the location if the exponent's negative.
So it would be A to the 4th power.
Okay, so why would it be, there's a couple of reasons why you could explain it, so I want you to explain to me why. Why is it a to the 4th power?
Because you can't move the top A because it's not a negative exponent, but you can add the one on the bottom to the top, which would make it.
Okay. All right, so one possibility that we have said is that we could move this up, and when it moves up as a cubed. We can add the 3 to the one that's there. That's okay. The other thing that you can do is you could use the property of exponents that says if I have an a on top and I have an a on bottom, I can simply subtract their exponents. So this is 1 minus, and then the exponent's negative 3 in the bottom. That's kind of the way I think about it. That works for me.
How
But
do
either
you
option
make it
works.
4 though?
Because 1 minus negative 3 is 4.
Okay.
Yeah. Or if you moved the a to the negative 3 up and it's a cubed, then 3 plus 1 is 4. Either of those work. What about those b's?
Can't you make b to the 4th be b squared and cancel out? Or
You could rewrite the b to the 4th as b squared, and cancel out a b squared. That would work. What else could you do? You could subtract. So you could do b and then do 4 minus 4 as your exponent. It's not 4 minus 4. I'm sorry. 4 minus 2 as your exponent, and subtract like that. Either way you do it, what do you get for your b's exponent? B squared. So you guys are thinking about it in lots of different ways, and that's okay. All right? It's okay. These down here, problem part B, don't have A as the base. All my examples before had A as a base. There's nothing special about A except that they have to match. They all had to be A to do anything with them, and this says 2/5 and 4/25, and they are not the same. So what are we going to have to do about that? We're going to have to make them the same.
it should be.
How could I do that?
Do you like solve each one individually first, like with the exponent and then make the bottom the same?
We could simplify each of them individually, but then we have to unsimplify them at the end because the directions told us to use them in simplest form with positive exponents. So I don't really want to multiply out 2 times 2 times 2 and 5 times 5 times 5 and then factor them at the end. It'll be a lot of work.
2/5 out of
Hmm?
You get 25, and multiply 2.
Okay, so can I multiply 2/5 by 5? Can I multiply the denominator by 5? Is that allowable?
This fraction is still the same amount, but it's just written what.
Okay, well, I could multiply 2/5 by 5 over 5,
Yeah, that's what.
but then my exponent, then my numerator doesn't match at all the other value, right? Are you guys with me? I want the numerator and the denominator to match. They both have to match.
So,
Okay, so you guys are recognizing that the 25 is 5 times 5. Let's talk about the 4 then.
It's 2 times 2.
It's 2 times 2. Right? Let's use that. So let me show you. I'm not going to change the first fraction. I'm going to leave it the same. What I am going to do is I'm going to take the second fraction and I'm going to multiply the factors there instead. Doesn't it already look more like the first fraction than it did before? I've got the 2's and the 5's that I wanted in it, right? What's another way of writing 2 times 2 or 5 times 5? Squared. So again, I'm going to leave the 2/5 to the third. And I'm going to write 2 over 5 squared. And then it still has that -6 exponent on the outside. Do my bases match now? Yes, they do. I have 2/5 on both of them. All right, what's next? They do, but I need them to be combined before I worry about the fact that the answer needs to be in positive exponents. So how am I going to combine them first?
Do you add like 2 to the -6?
Do we add?
you multiply 2 and 6.
We multiply, yeah. So I'm going to multiply these two together. Okay, so I have 2/5 to the third, and then I have 2/5 to the -12. Now what?
You're gonna do -12 times 3?
Negative
No,
12 plus
negative
3.
time, -12 times plus.
Plus, yeah, so I'm going to add my exponents now. So now I have the 3 exponent and the -12 exponent. So what is 3 plus a -12? That is -9. Okay, this is simplified, right? I've got it as sort of as compact and small and combined as I can, but I do have one more piece of the directions that you were mentioning before, Leah, that exponents being positive business. How do I deal with that? Yeah, I can flip it. So this is actually 5 over 2 to the 9th. Or if you want to, you can write it as 5 to the 9th over 2 to the 9th. Either of those would be considered the simplest form of this rational expression. All right, we're going to go one step further in solving, exponents to solving. Solve for n if possible. So, all the problems that we're going to do in solving for n if possible are going to involve us looking at the fractions and getting the same not the fractions, but the exponential expressions and getting the same base. Our goal is always to have the same base. So on the first one, on part A, they all have the same base, right? Agreed? They're all base 2. The next goal is to get them each side to have only one base. So I'm good on the right, not so good on the left. How can I rewrite what's on the left-hand side so that it has only one base?
2 to the 7 plus 7.
We can add the exponents. Okay, now the right-hand side, even though my left-hand side had the matching bases, the right-hand side doesn't have a base yet, right? It's just 64. I need it to have a base, and the same base I already have. I need it to say 2 to some power. So you got to experiment with it. Grab your calculator, see if you can try. 2 raised to a power. What power will it take to give me 64? Bigger. Smaller. 6th works. Very good, Audrey. 2 to the 6th. 2 to the 6th is the right value. And nobody, you guys were kind of guessing a little bit, but really you figured it out, Audrey, by using trial and error in your calculator, right? You guessed what you thought it was. You tried to see if it worked. Okay? That's all we're doing with these. If the bases are the same, we can compare the exponents. What would n have to equal in order to make the exponents now the same? -1. Is everybody with me on that? Second problem. Left-hand side, single base to a single exponent, but the right-hand side has a fraction, which is already weird. And I mentioned just a minute ago that all of your problems are going to have the ability that they can be the other base to some power. So let's ignore the fact that it's a fraction for the moment and just pretend that it said 81. Can you do that with me? Just pretend. How could I rewrite 81 as 3 to some power? So this is the same question that we encountered with the 64, right? The fourth will work. 3 to the fourth. So this is 3 to the fourth power. These are equal values. Now what am I going to do because the 81's in the denominator? It'll be -4th. So this is 3 to the n on the left. This is 3 to the -4th on the right. And it is a less than or equal to between them. Now when I compare my exponents, they don't even need any simplifying, right? Any idea what I might need to put between them, though? What symbol needs to go between the n and the -4? No? What'd you say, Catherine?
Smaller and more equal to.
Okay, this symbol that's already there, the less than or equal to one? Yeah, that's the one we want. Okay? Whatever the symbol is that takes the original problem will be in your answer as well. Okay, so you just follow suit with what's there. And we have n is less than or equal to -4. And we're going to do a couple of examples of exponentials used in context. Before we do that, we have an approximation one again. Sorry, I just looked right over that one. Approximate. This one's easy. 20 1/3 divided by 9 7/8. What is that approximately? Don't overthink it. 2. How did you get 2, Abby?
Because 20 divided by 10.
Yeah, you're just thinking that 20 1/3 is about 20. And 9 7/8 is about 10. So 20 1/3 divided by 9 7/8 is approximately 2. That's all. Just an approximation. You guys probably do that sort of thing in the grocery store when you're trying to make sure you have enough money to pay out. You kind of approximate a little bit as you go, especially if you only have a few items, kind of a deal. All right, a couple of examples in context now. This is where I was headed. Jasmine is reading a book. She has 1/4 of the book left, and she has read 246 pages. How many pages does she have left? There are several ways to set up the problem. Okay, you want to do what? 246 divided by 1/4. Okay, what will that give me? I mean, I don't mean what number, but what am I going to find out when I do 246 divided by 1/4?
You have to find out what 1/4 is.
No, because the 1/4 is the 246. And we already know what that one is.
How much do you have left?
Nope, we're not going to find out how much we have left either.
No, 1/4 equals 246, so then you have to multiply it by 4, so you'd have to flip it.
Like that? Okay, so the 1/4 would be 1/4 of what? Okay, so 1/4 of the pages. So can I call it P for pages? P is our total pages. Total number of pages, actually. So 1/4 of the total number of pages equals the 246.
If she has 1/4 of the book left, she's read 246 pages, so that means 246 pages is actually 3/4 of the time.
Okay, Good point. So has she read 1/4 or has she read 3/4? Okay, so if I find the 1/4 part, that's okay. I'm just not going to be answering the question that's exactly asked right now, right? So I think, Catherine, you're suggesting maybe we want to do a 3/4 here. Does that sound right? Okay, so it says she has 1/4 of the book left and she has read 246 pages. So she's actually read 3/4 of the book. Are you guys with us? Make sense for everyone? Okay. All right, then what would I need to do in order to solve this particular equation? Good. Multiply by 4/3. Okay, so I have x on the, or sorry, not x, p on the left. And then you guys are going to tell me what in the world is 246 times 4/3. What was it? 328. So it would be 328 what? Pages? Total. So that's like the total pages in the book, right? Is this not what you got, Madison? Okay, what number did you get?
I already started running the 1/4 thing,
Okay.
so I got something way different. I got that there were 984 pages total.
You got 984 pages total in the book.
Yeah.
I got that before I divided it by 3.
Yeah, because she's had 3/4 of the book that she's read.
Oh, she's read 3/4.
Yeah, are you good now? Okay. 328 pages total. But what was the question that was asked? I don't think that was quite what was asked, right? How much do you have left? So what would have to find out? Subtract. So 328 minus 246. So if I subtract, what do I get? So there are 82 pages left. Okay, you guys good with that? Okay. I think this is, yes.
Do we have to write it out like that? Or, because when I first started, I said as 3/4 is equal to 246 over x.
You set up as a proportion.
Yeah.
That's wonderful. We're going to get to proportions in section 6.4, so you're ahead of the game. That would be just fine. You're doing great. Yeah. All right, let's take a look at this one. Al gives 1/2 of his marbles to Jose. Jose gives 1/2 of his marbles to Isabel. Isabel gives 1/2 of her marbles to Letitia. Letitia was given 4 marbles. How many marbles does Al have now? They should just all hang on to their own marbles, don't you think? Like, for real. All right, let's write down our names of our characters in the play, and we'll figure out what's happening with them. We started with Al. And then Al had a conversation where he gave away some marbles to Jose. And then after, I'm sorry, was he Isabel? No, that's right, Jose. And then Jose gave marbles to Isabel, who turned around and gave marbles to Letitia. Is that it? Did I get them all?
Yeah.
Okay. So, now what? Do we find out where they started, or should we maybe find out where they ended? We're going to need to know both, right? Letitia has how many when the whole process ends? 4. And those 4 came from Isabel. And when Isabel gave her those 4, how much of what she had did she give away? 1/2. So how much did Isabel have before she gave away her 4? 8. But Isabel got all 8 of those marbles from Jose. So how many did Jose have before he gave them away? 16. And then Jose got all of his marbles from Al. So Al would have had 32. So Al had 32 marbles when it started. How many marbles does Al have now? So be careful to answer the question that was asked. Al now has 16 marbles. All right, any questions on that one?